In the problems we've been doing, our goal has been to find the extreme values of these functions and where they occur. So in problem number 50 here, the function is e to the x minus e to the negative x. And just to give you a little idea of what that function might also be written as, let's deal with this negative exponent. That's really 1 over e to the x. So the function is e to the x minus 1 over e to the x. And the first thing we need to investigate is the end behavior of this function. So we want to know what's happening when x approaches infinity. So what's happening on the right side of the graph. And it's pretty clear that when you plug in infinity, you get infinity minus 0 here, which is still infinity. So this thing takes off without bound on the positive side of the plane. If we take a look at the other side, as x approaches negative infinity, this function is actually going to behave a little bit differently. The e to the x actually becomes e to the negative x, because the e to the x is heading towards, the x is heading towards negative infinity, so this would behave like a 1 over e to the x. In other words, this term is going to be heading towards 0, and this one's going to be heading towards infinity, and this turns into a negative infinity. So the behavior of this function at the extremes on the far left or the far right is, on the far right it's heading off to positive infinity, and on the far left it's heading to negative infinity. That's just good to understand what's happening at the extremes so that we know whether or not we have any absolute maximum or minimum values. What this tells me is I'm not going to have an absolute max or an absolute min, because this heads towards positive infinity and this heads towards negative infinity. We still need to find out what's happening in the middle of this function. And for that, we're going to look at critical points. So let's compute the derivative of this function, f prime of x. The derivative of e to the x is e to the x. And the derivative of negative e to the x, e to the negative x is negative e to the negative x. So that's going to turn into a plus e to the negative x. So this is our derivative. And it's hard to tell what's happening with this derivative when it's written like this, but let's turn this into the fraction form again. So this is e to the x plus 1 over e to the x. And we can get a common denominator of e to the 2x over e to the x. So let me show you what I mean by this. If I get a common denominator of e to the x here, that means I'd be doing e to the x times e to the x, which is just e to the 2x. You add the exponents. So this function, this derivative function, is actually e to the 2x plus 1 over e to the x. And the question is, are there any undefined values in this derivative? And the short answer is no, because e to the x is always positive. And can this numerator ever equal 0? And the answer is no, because e to the 2x is always positive, and positive plus 1 is still positive. So this is never 0. So there's never a 0 and there's never an undefined value. So what that means is there are no critical points. And that happened because when I set this equal to 0, there's no zeros. E to the 2x can never equal negative 1. Okay, so there are no critical points, and this thing grows without bound in the negative direction on the left and the positive direction on the right. What that tells me is there are no extreme values to this entire function. So the answer for the entire problem is no extreme values, no extrema. How do you spell that? O-E-X-T-R-E-M-A. No extreme values for that particular problem. That's interesting. They asked us to find the extreme values and stuck us with a function that doesn't have them. But it's possible that might happen. So this is how you investigate that. Let's try another example. Problem 54 is a bit of a stinker. It has a couple of functions that we don't have a lot of experience with. One of them is e to the x, and the other one is this inverse sine function. So what you need to know about the inverse sine function is that the domain of the inverse sine function is between -1 and 1. Let me write this a different way. I'll write it in interval notation, -1 to 1. Those are the numbers that we can put into an inverse sine function. So what that means is that whatever the output of this e to the x function is, it has to be in this range. And I happen to know that the e to the x function crosses the y-axis at 0, 1. So when you plug a 0 into e to the x, you actually get 1. That means that for e to the x, this x here, this x, the yellow x from this function, it cannot be bigger than 0. So x is going to be less than or equal to 0. And on the other end, the function e to the x is always positive, so it's always going to be in this range in here, as long as we stay less than 0. So I don't have to worry about going into the negatives. We're okay going this way, negative, all the way to negative infinity, but we can't plug any number in that's bigger than 0. So this whole entire function here has a domain of x is less than 0. I'm letting you know that because that helps us decide what's going on with the end behavior. Essentially, what we need to know is what's happening at this end point here of x equals 0, and then what's happening as we head towards negative infinity. So I'm going to go ahead and compute f of 0 because that's easy, right? F of 0, and oh, it's not going to let me do that. Sorry, I'm just talking to myself here. F of 0 is just going to be the inverse sine of 1, which is pi over 2. Right? When you plug 0 into e to the x, you get 1, and the inverse sine of 1 is pi over 2, because the sine of pi over 2 is 1. Okay, now the other end that we have to check is the limit as x approaches negative infinity of the function f of x. And I'm calling this thing f of x. F of x equals inverse sine of e to the x. I can actually figure this thing out too. As you send x to negative infinity, e to the x heads to 0. And the inverse sine of 0 is actually 0. Now keep in mind, we're never going to get to 0 in terms of the y value, but we are approaching 0. So that's what's happening with the end behavior. The other thing we need to do is see if there are any critical points. So I need to know the derivative of this thing. So we've recently studied the derivative of the inverse trig functions. The derivative of inverse sine of u happens to be u prime over the square root of 1 minus u squared. So u prime in this case is going to be e to the x, and that's going to be over the square root of 1 minus e to the x squared, which is e to the 2x. Sorry about that. And then we're trying to find places where the derivative is 0 or undefined. When you have a rational function, in other words, when you have a fraction, the way you check to see if a fraction is equal to 0 is you see if the numerator is ever equal to 0. So I have to solve e to the x equals 0, and that is that there's no solution to that. So there's no critical point here. To find out if a fraction is undefined, we're looking for places where the denominator is 0. And essentially that's going to happen when e to the 2x equals 1, right? Because if this turns into a 1 here, then I've got a 0 in the denominator. And we can solve that. That's going to happen at x equals 0. So x equals 0 is a critical point, but we already had x equals 0 as an endpoint. So this critical point really is useless to us. So the only important points we have in this function are 0 and then this limit here. Okay, so what does that mean? That means that we do have an absolute max at pi over 2. And the reason I know that's max is it's higher than this 0 here, which we're never really going to achieve anyway. So the absolute max is at pi over 2. How do I spell that? Absolute max. It occurs at 0, and the value is pi over 2. And then there is no local or absolute minimum for this function. Because as x gets closer and closer to negative infinity, we get closer and closer to 0, but we're never going to hit 0. For any number greater than 0, I can find an x value that'll achieve that. And so I won't be able to, we're not going to have an endpoint there where we have an absolute minimum. Let me show you a quick graph of this thing just so you can see that I want to visualize what I'm trying to say, I guess is what I'm saying. So you'll see I'm not crazy. I might be stumbling with my words, but I'm not crazy. Take a look at this graph. So here I've entered in our function, the inverse sine of e to the x. And notice that the things that we found are actually true here. So this point right here, that's the 0 pi over 2 that we talked about. Notice that there's no function over here anywhere, because this function is not defined for numbers, for x values that are greater than 0. So we have this y value at 0 pi over 2, and then all of the other y values, which are this red curve here, right? It's getting closer and closer and closer and closer and closer to 0, but it's never going to hit the x-axis. The x-axis is an asymptote. And so there is no minimum value because it just keeps getting closer and closer and closer to 0. There's a boundary, which is, the y equals 0 line, but there's no minimum value. We can just keep getting closer and closer to 0, but never actually arriving there. So this graph shows visually what we were trying to describe with our work in the last slide. That we have an endpoint, so we test that y value, which is pi over 2. All of the other y values are less than pi over 2, so that y value is an absolute max. It occurs at 0, and the value is pi over 2. And then there is no minimum y value. Okay, hopefully that helps you with a couple of more challenging examples. Keep in mind, you can always pop this thing into a graph and peek at it if you need to get an idea of what's happening with the function. It'll take practice, but you'll get better at analyzing these functions and figuring out where these extreme values occur. Okay, if you need anything, you know where to find me. In the meantime, take care.